specific, or we're not doing specific heat specifically.
We're going to do specific capacities there.
Specifically, but within the internal energy equation, right?
Mm-hmm.
Alright. So, Meg, you don't understand what? You don't understand what this is, this, or this, or this? I think you know what this is.
Yeah.
Should know what this is.
Yeah.
Should know what this is.
Yeah.
Maybe, so then this is the one. Internal energy is the energy that we have due to
Friction, heat, what?
yes, kind of the second one. She said heat, kind of, not really. Internal energy is the energy that we have due to what causes heat. Or what's a result, I should say, of heat.
Temperature, movement,
Movement of
particles.
particles. Internal energy, and that's the way that I remember it. Because internal, inside, internal energy is U. That's the energy due to particle movement. Now, the reason that I said you were kind of right, Anna, with heat is because...
It causes heat.
It causes particle movement.
What's that? Heat... I don't know, I'm not gonna... Well, does heat cause particle movement, or does particle movement cause heat?
It's like saying which one comes first, the chicken or the egg.
Kind of, it's more like heat causes particle movement. Because if something is going to go up in temperature, then the particles are going to move faster.
Then what causes heat?
What causes heat?
Yeah.
Energy.
Which means you need particle movement.
Well, the particles move faster as a result. But that's the thing, is we're not going to get super in depth with this. But basically, the reason that we have a rise in temperature is because there's more energy. There's more energy. You don't necessarily feel it in your body, because frankly, your body is always the same exact temperature. So you do feel it actually when you stray from 98.6 degrees or 36 degrees C. That's when you start feeling like crap. Like when you were sick, your body temperature is off. Now, when you're hot, technically you have more energy, sure, but a lot that goes into, I mean, you guys talk about it in biology. When you're sick, part of the reason that your temperature is going up is because your body is fighting. Your what system is that? Your immune system is fighting, and hence those particles are moving faster and having more energy because they're working to destroy whatever it is inside of you. Now, when you're cold, like there was they talk about people that capsize in the Atlantic Ocean. And after a while, you can actually live 70 degrees, your body temperature. Now, once it gets down, because they sit in the water that's about, 50, 60 degrees for a long time. Well, what does that water do?
Cools down your body temperature.
No. Well, yeah, but your body's actually... Correct. Your body's attempting to heat up the ocean. Obviously impossible. But when your body actual core temperature cools down so much, it literally is the amount of energy that you have is depleting. Your particles are moving slower on the inside, which is why you then start to shiver.
It's also why your fingers and toes get numb.
You start to
go into them.
Right. You start to shiver. What's shivering doing? It's actually muscles that are, that's this, trying to create this.
Yeah.
You're using calories body calories to try and create internal heat so that your organs don't kaput. But you can be in the water. There's a story. It depends on your BMI. It actually, the fatter you are, the better it is if you ever get stuck in the ocean. There was 3 NFL players that capsized, and actually there was two NFL players and their buddy, and the 2 NFL players were the first 2 to die. The guy that was less in shape was the one who ended up surviving, because the 2 guys that were in great shape, they were all muscle, muscle and bone, little fat, like 5% body fat, and so there was little insulation because fat is a better insulator than is muscle.
Plus, they were more dense, and it was hard for them. It worked harder to stay afloat.
Well, no, the boat was still there. The boat was capsized. They were all resting on the boat.
Got it.
But they just, they ended up dying of. Well, they said they went delirious. There's a book that I wrote about it, but it's weird. Your body does weird things when it gets very cold.
Yeah, the last stage of hypothermia, you actually feel like you're really warm, and you're in a state of delusion.
Right.
And you take off all your clothes and run around and say.
They said that the last part, they were just like literally like looking like a rabid dog, just like spitting and all this like running around, and then at the end they just like pushed themselves off the boat, which there's big waves, and so obviously the boat was what was keeping them alive. Pushed themselves off and were like, I can swim, and then dead. So, but anyways, internal energy is energy due to particle movement. So when they give you, like for example, well, give me an example out of the book. It's like when an egg, which is up here, goes splat to the floor. All right, what does it have up here?
What kind of energy?
Potential.
It has PE. Anything else? It has U.
Oh.
Everything's got some U. At least a little bit of U. So it's got some U. Now, when it falls, what happens?
It gains kinetic energy.
It gains kinetic energy. Here it's got a bunch of kinetic, just a little bit of potential, and obviously also some U. At the bottom here, what does it have?
Nothing.
No PE, no KE, some U. Now what's the U from?
From the movement before?
Yeah, the U is from the friction that it just gained by going splat. It's gonna have increase in temperature just a touch. Now, the last part that we need to take into account here is that a lot of the energy was expended by doing the work that it took to. What work was done from here to here? What is that egg going to look like down here? It's not going to resemble much of an egg. I had a hard-boiled egg this morning for breakfast. And what do you have to do to get the hard-boiled egg? You have to do some work. What work?
Peel the shell.
You have to crack the shell. There's much work. You can squeeze a shell, an eggshell like this, and I bet you, well, it depends how big your hands are. Anna and Sue, I bet you guys can't smash an eggshell in your hand like this. You just squeeze it. All your fingers just squeeze. Try when you get home. If you do, it's funny, the yolk shoots out. But I learned that the hard way home back once. Somebody told me I couldn't do it in high school. Squeeze it. Yolk flies across the room. My home ec teacher was standing there like it was perfect, but it sucked. right in the middle of her chest.
I wouldn't so
Everyone was like whipping out. Who was that? It was awful. She was not a happy camper. But anyways, there's work done to crack an eggshell. And so this is true. And the one output that we can have from this is work. So if you say that the energy is not matching up, that means that it left to work. We have one more equation that we put on the board. Q equals U minus W.
Isn't it U equals Q minus W?
Yes, my bad. Thank you. You are correct. U equals Q minus W. What is Q?
That was changing temperature.
Heat.
Oh.
W is work. And so that's what we're talking about here basically, is that this U, although you're not, it's not like you're gonna run here and after you drop an egg from the top, you're gonna take the temperature and go, oh, look at that, it rose 7 degrees. That doesn't make sense. It didn't. Though where that U is going is right here, is work. Because it takes work to crack that shell. Okay? So, what specific questions have we on the homework?
Any?
Any?
I would check number 2.
Number 2?
We're working with the railroad spike.
Yeah.
Alright. 500 kilogram spike, he drives it in with a 2.5 kilogram sledgehammer. The sledgehammer hits the spike with a speed of 65 meters per second. If 1/3 of the kinetic energy is converted to the internal energy of the hammer and spike, how much does the total internal energy increase? Of the system, that means.
Hold on, 1/3 of...
The hammer's kinetic energy,
Oh,
which is based on 65 miles or meters per second, and a railroad tie, which is 2.5 kilograms. Or the
2.5?
The hammer's 2.5, sorry.
alright. Good?
Yeah.
1/3 of the hammer's kinetic energy is transferred.
1/3 of the kinetic. Oh yeah.
Yeah. With sledgehammer.
Okay?
But it's converted into the internal energy of the hammer.
Right.
I think it would help to do an initial and final here. Energy initial, energy final.
That's important, that last part that you said, Sue. Because how much of the hammer's kinetic energy is transferred? What?
Whether.
How much of the hammer's kinetic energy is transferred?
Oh.
All of it. How do you know?
Because it moves the name.
No. How do you know all of the hammer's kinetic energy is being transferred?
It stops.
It stops and... No, this is an easy two-column proof. Number 1, hammer stops. Number 2, the basis for everything in physics. The basis for everything in physics. Newton said... Oh man, you guys are Monday today.
Oh, wait. Wait.
Come on, Monday.
For every...
There's so many things you could say here, but the basic one that I'm looking for is blank cannot be blanked or blanked.
Oh, energy cannot be.
Yeah, energy cannot be created nor destroyed, and hence, so since we know the hammer has kinetic energy, we know that it's going to stop right here. Every single bit of it is being converted into something. 1/3 of it is being transferred into the U of the nail.
Actually, it's the U of the system. It says the internal energy of
Okay.
the total internal energy of the hammer and spike.
Okay.
And that's why I think it would be good to do an initial and final. So we see what types of energy we have
Correct.
initially, what we have final.
Because remember, we said that there's 2 forms to write that equation, Nick. Yeah.
It's the same thing as energy initial equals energy final. We did it with mechanical energy. We haven't done it with.
So UI plus KEI plus PEI equals UF, yada yada yada, right?
So what do we have initially? What types of energy initially? What does the spike have?
UI.
As U, yeah. What about the hammer?
KEI.
Right. But what else?
UI.
Yeah. And that's the hammer again. Is that it on that side? What's final?
UI for both.
Say what?
UI for both.
Okay, both. Good. Is that it?
Yeah.
Pretty much, yeah. Now they're saying 1/3 is going to be converted to this. Honestly, I mean, they're saying on impact. So what's going to happen on impact? Not only is some energy transferred internal, but some of that energy is going to stay kinetic and drive the spike down, right?
Yeah.
Okay. We're only working with the change in U, which is nice because we don't know the initial U, do we? We don't know how much energy it already has. We don't know a temperature. We don't know a density. We don't know what the materials are made of. So we have no way to find exactly how much internal energy they have right now. But that's okay because we're looking for this. Okay? We're looking for the change in it. So we can ignore what's already there and just say, all right, 1/3 of that kinetic energy is going to become internal energy for both. Okay? So simple as that.
So we'll just use a mass on the hammer.
Because the hammer is what's being swung, okay? And the energy from the hammer is going to go into both. Some stays with the hammer, some goes with the spike.
So the mass of the spike doesn't matter.
Not really, no. It would matter if they asked us how fast that would be moving after that. I mean, we could argue that, okay, if 1/3 of the kinetic energy is transferred to internal, the other 2/3 must remain kinetic and thus go toward the mass of the spike and move it. We don't have to worry about that part. That's nice. So what do you come up with?
1,760.
There you go. Joules, we're talking about energy here. So that's the change. That's the change in U. And this should make a lot of sense now too. This one up here, change in U is heat minus work. This became heat, right? Well, how come this only changed by this much? What happened to the other 2/3? Yeah, it stayed in motion. Yeah, driving the nail into the ground. Okay. Change in internal energy is Q minus W. So there was some heat, but some of it was also lost to work. Any other questions with those? Well, any other questions about those? How about number 4? Did that go okay?
I don't know. We should do
Number 4 is a fun one.
Okay. What was the answer for that?
Number 4? It's a very small number of. It's a very small mass.
Mass.
Yeah.
1.23.
Say what?
1.23.
Times 10 to the something?
No.
Oh.
We do that.
We're not seeing how much the mass is, though, is it?
Oh, wait.
No, they gave us the mass already.
How much ice melts? So what's the mass of the ice that melts? That's what they're asking for.
Oh. I found the amount of energy that it took.
Okay. Can you find mass from that?
Like, well,
Times 10 to the negative 4.
There you go, Sue. So how does that all work? What do we do?
How did you forget that the first time?
Because I don't,
No work! No work.
I don't do 10 to the blah blah and calculator.
You do that all the
Just
time.
enter all the.
Got it. Because it doesn't matter. You just have to keep yourself organized and not forget to put it.
Yeah,
Sue
yeah.
does sign limitation for everything. For 10, she puts 1 times 10 to the first. I mean,
Do you?
what?
no, I'm just kidding.
Oh,
I was gonna say.
it's a little
That's
weird.
kind of silly.
Yeah, make sure you do that.
All right, let's do it before or after again. What are you doing to the ice initially?
Nothing.
Or what is the ice doing, I should say. What is the ice doing?
Nothing.
Say again?
Nothing.
No.
Sliding.
It's sliding, yeah. It's sliding.
Oh.
So, what kind of energy? Yeah, you just said it, kinetic. And then some of that energy through sliding is going to go to melt the ice. Why? This is easy.
Because there's friction.
Yeah.
Let's see.
So we're going to change internal energy, we're going to add internal energy, and some of that internal energy then will go toward melting. Okay? Make sense? This is all we're worried about. So, they give us how much is required to melt 1 kilogram? Okay, so we'll deal with that later. First of all, let's just find out how much heat is actually given off, okay? Or how much work, how much internal energy. It says 3.3 times 10 to the 5 joules are required to melt 1 kilogram of ice. Now we have 2.5 kilograms. Do you think by sliding all of that's going to be melted? That's a pretty big block of ice. 2.5 kilograms of ice. That's like 10 pounds of ice. It's a big block. You think all that's going to be melted just by sliding across the floor?
2 kilograms?
Yeah, 2.5 kilograms. Do you think it will all be melted?
All of
Like
it?
5 or 6
No.
pounds of ice.
10 pounds, yeah.
10?
I think. Oh, 2.2. I was thinking, yeah, okay, I was thinking newtons. Yeah, okay, 5 or 6 pounds of ice. Still. Think that's all going to melt?
No.
No.
Alright, and that's why they ask us what portion of the ice, how much ice melts. Okay? So if we know that this much ice melts 1 kilogram, we have to find out, we'll create a proportion. Okay, we're going to find out how much energy is internalized here, and thus that can go toward melting 1 kilogram, or 2.5 kilograms, or we want to look at it, but it might not get the whole thing. So kinetic energy initial, and again, this is the easy part now, 1/2 mv squared. So what is the initial kinetic energy? Once that thing stops, once that ice stops moving, how much kinetic energy has been transferred to internal? Because all kinetic energy is going to go somewhere. Because the thing won't slide forever, even if it is relatively frictionless because it's ice. It won't go forever. So how much energy is transferred?
All of it.
Huh?
All of it.
Right, what's the, give me a number.
3.3 times
What'd you say?
10.
No.
And if all the energy?
16.25.
16.25? Okay.
Oh, so I did find part of it.
Like that?
Mm-hmm.
Alright. Well, then, that's going to convert entirely to internal energy, thus it's going to raise the temperature and start it melting. I'm not sure I agree with that number though, AJ. Did you square the velocity?
We should. No, I didn't do it right.
So it should be. So what do you have?
40.61.
Okay.
Yeah.
Nowhere near 1 kilogram, right? So this is going to melt just a tiny, tiny, tiny bit of ice. How much? You have 3.3 times 10 to the 5th melts 1 kilogram. How much does this melt? Just a proportion. Does that make sense, Anna?
Yeah.
Now, I like this question because they're preparing us for the next section on calorimetry, which is dealing with calories and specific heat and internal energy transfer, making things change phases, and how exactly how much it's going to raise temperatures. So this is kind of a preparation. They're priming you for it. So you should get a very small number for number 4. Number 5, what do you guys think for number 5?
41.
Okay, and you were able to work it out without, obviously the answer's in the back, but you guys were able to work that out okay?
Yeah.
Alright, cool. How about, did you do the bottom of the page, or
Jesus.
was that something else?
Supposed to?
I don't remember.
Yeah.
No? Okay.
Yeah, I don't think so.
You were supposed
Alright, do number 4 right now. Water at the top of nitrogen falls at a temperature of 10 degrees Celsius. Assume all the potential energy goes to increase the internal energy of the water, and it takes 4186 joules per kilogram, that's a specific heat capacity right there, to increase the water's temperature by 1 degree Celsius. 5 kilograms of water falls 50 meters. What will the temperature be at the bottom? So you're going to find how much the temperature rises just by the water falling. It's kind of funny to think about. You know what I'm doing right now? I'm heating up my water. I'm making it warmer.
It's true.
This is what I transfer to it. Kinetic energy. Kinetic energy of my hand shaking increase the internal energy of the water. There's actually no water in there, but you get the idea. Agitation.
So I got like 69.17 degrees Celsius.
Whoa, I'm just gonna raise that much.
No, it's not. I don't know why you
That's
got
That
ridiculous.
would be crazy.
Alright, let's do it before and after again. What kind of energy does it have before it falls?
Like shake the air, push these ice down and like burst into flames.
The water's gonna begin burning.
Yeah, it's boiling. How much of the ice melts? All of it melts and half of it boils.
10.117.
What'd you say?
10.117.
What? Eiffel Tower? Cats?
Celsius.
Degrees?
Yeah.
Yes, the final temperature, 10.117 degrees Celsius. Okay, how'd you get that, Sue? And put it way down here.
Yeah.
Is it what you got to?
Nope.
Okay. Well,
Wait, how do you do this?
MGH. How much potential energy did the water start with? That part's easy. AJ, what'd you get for that? How many joules?
Like 24,000, no, 247,000.
Okay, good.
225.
Oh, I think I'm.
So now once you have that number, so we have an amount of joules, 247,000. What was it?
702.5.
Okay. 247, 702.5. That many joules of energy now is going to raise the temperature of the water. Now, it takes 4186 of those joules to raise every kilogram of water 1 degree. How much water is there? A crap load of kilograms, right?
Yeah.
Crap.
This
son.
is joules in how many kilograms?
505.
No, 4186 joules per
One.
1 kilogram.
Wait, how?
You have 247,000
I
joules.
got,
How many kilograms? What, Sue?
I got 247,702.
Mm-hmm. I may have said that wrong, but that's what it is. 247, 702.5. And then,
Ugh.
how many kilograms of water do we have?
I got 10617.
507.
Mm-hmm.
Um.
Meaning that,
Ha ha ha.
okay, this results in an increase of 1 degree Celsius, right? So this results in a change of this many joules over 505 kilograms isn't nearly as many joules. You know, not every kilogram gets 4186 joules, so it's not going to do much. 0.017 degrees Celsius, that's how much that changes it, or 0.0117
Yeah.
Celsius degrees. Therefore, if the initial temperature was 10, final temperature,
Where
10.117.
do you get 0.117 now?
That's what.
This is, let me redo this here. This results in an increase of 1 degree Celsius, right? 46 joules per 1 kilogram of water gives you 1 degree of temperature change. Well, you have this, but how many joules per kilogram does this come out to be? Convert that to per 1. Divide this by 505.
490.5.
Wait, what?
5.
Okay. So, AJ, you have 490.5 out of 4186. It's a fraction. You raised the temperature of the water 490.5, 4186. So you're just making that fraction make sense.
Yeah.
In other words, roughly 1/10 of a degree. Don't worry, this is tricky because we haven't dealt with this yet. Now that we are, it's going to make stuff like this much, much easier. Okay? Because we can just plug it all in here. I'll give you an example. Let's do this one with this equation. How much heat was added to the water just by it falling?
117. Oh, that much joules.
Yeah, we want heat and energy, yeah. The mass of the water was 505 kilograms. The specific heat capacity of the water is 4186 joules per kilogram. In other words, that's how many joules it takes to raise 1 kilogram of water 1 degree Celsius. That's a calorie.
Wait, what's MCP mean?
This is the specific heat capacity, and remember the P means that we're at a constant pressure.
Okay.
M is just mass, change in temperature. So, find the change in temperature and see what you get.
Oh, it is.
You should get the same
Yeah,
thing.
it is the same. That's exactly what I did.
Good. So you used that already.
Yeah.
Okay.
That's okay.
Well, that's all the next section is about, calorimetry. Using this equation to find out how much different specific heats change. Now where it gets a little tricky is when we're talking about two substances equalizing. Think about dropping ice cubes into a glass of warm water. What is going to happen eventually? Actually, no, don't think of that. Think of dropping a chunk of hot iron into a glass of water. What's going to happen?
Iron's going to cool, vary. And water will then fly.
Because
Good.
Mm-hmm. And so, they'll, what temperature will they both eventually become? The same.
yeah.
Not even next temperature. They're going to equalize, right?
Okay.
Nature creates equilibrium. So,
I thought you already kind of said that by both of them being.
that's all right. All right, I dump a chunk of, okay, here's a container of water, which is at, let's just say it's at 0 degrees Celsius. We'll say it's very, very cold, ice cold water, but no ice in it, okay? Let's say that we drop in a chunk of iron that is initially 400 degrees Celsius. That might be past the boiling point of iron, melting point. Let's go 200. All right, so what temperature do they equalize to?
Depends how big the iron is, isn't it?
Well, 0 to 200. Why can't we just average out to 100?
Because it's not that proportional.
Why not?
Because it depends
On what?
on the mass of the iron and how much water you really have.
Okay, let's say I have. Okay, iron's pretty heavy, right?
Yeah.
Let's say I have 1 kilogram of water and 1 kilogram of iron.
If you drop in it, the water will go
Okay,
up.
say the water won't splash. Okay, we're placing there gently. Okay,
No, but
and
just
the container is big enough so that the
No,
water
but
will
then
displace over the edge.
like when you do drop it in, the movement of the water will make it like heat up. even
Ignore
more.
potential energy.
First, they're so persnickety.
That's good. This is cool.
But I'm saying, given the fact that
There you
some
go,
of
answer.
the other things that we get from them, it's like, you forgot your name. You didn't label. What is it? Cat's Eiffel Towers? Oh, that doesn't matter. Well, actually, Mr. Gottschalk, if we...
They got out of that money
It's
pretty
true.
quick. That's good.
How are you going to put the iron in that tall glass without it splashing?
Yeah.
Tongs. And the tongs are made of something that is 100% insulation, so no energy can be transferred to the tongs.
That's awesome.
Boom!
In a perfect world where none of this would exist. what would-
Right. In a perfect world, in a closed system where there is no air here, and somehow the iron spontaneously appeared inside the water at a higher temperature, not displacing any water, just appearing and adding to it. What happens to the temperature? Oh, it'll be 100 then?
Yes.
I think so.
Okay.
No.
No.
Why?
You focus
That
on all
would be
those
silly.
little dinky
That
stuff.
would mean that you would die every winter and summer.
What's
Oh.
Why would you die every winter if that was
Yes,
needed?
Trying to reach equilibrium with it.
Because you would walk outside and all of a sudden you'd be 40 degrees
That's
Fahrenheit. Because you were 98 and it was -10, so you guys equalized instantly, boom, 40 degrees.
So it depends on how
Keel
much
over.
work it takes for
Depends
each.
how big each is. Think about this. If you dropped that piece of iron in the ocean and it was 200 degrees, if it heated the whole ocean,
Well,
right?
if the masses are the same.
are the masses the same?
Yeah, you
Yeah,
just
we
said
said
that 1
the
kilogram, 1
Yeah, so
kilogram.
1 kilogram of each.
nice?
So the mass is the same. Yeah, why not, right? Turn to page. No, not 371.
It depends, guys, on what.
And the actual size?
No.
No.
If
Look
you
at
dr-
this
if you-
equation and tell me what depends on. Look at this equation.
The specific heat.
Yes, we've
Yeah,
talked
just
a lot
about
about these. Well, just specifically to water, we've talked about specific heat.
That's water, not iron. Right? We need to know not only the amount of iron, but we need the specific heat of iron. There's a list somewhere in here. I can't find it.
270s or
37.
what was it? We were on it the other day.
I know we were.
72.
It's
72.
372.
Oh, it is.
72.
Okay, 372. Perfect.
Oh my god.
Is that what you said, Sue? Because I thought I said
No.
371.
No,
She
I
said
Yeah, you were
said
wrong.
Yeah, she was wrong.
All right.
I don't know what she was
Look at
looking for.
So now, if you know the specific heat of iron, now we can find out, right?
Sure, yeah.
How do I use this equation to find out?
You match both of them?
What do you
Just
mean?
like, set them equal to each other?
Yes, good. What happens is one thing's going to lose energy, right? And one thing is going to gain heat energy. You set the two equal. Now, why do I have them equal? Shouldn't one be positive, one negative?
Because we're trying to find what the equilibrium is. And so they will be the same.
Yeah, and we're talking about energy, and energy is not negative. That's the other reason. But yes, equilibrium. So, in other words, the amount one loses will be the amount the other one gains. So, loss. What's losing energy?
What?
What's losing energy if I'm dropping a chunk of iron in?
Iron.
Iron is losing heat, yeah, and so the water is gaining, right?
Yeah.
So on this side we have the mass of the iron times the specific heat of iron, which is what, 448 or something like that?
Yeah, 448.
Joules per kilogram. Remember, that means it takes that many joules to raise 1 kilogram of iron 1 degree. So it takes less joules to raise the iron's temperature, or lower it, than the, yeah. Okay.
Changing heat.
Equals mass of the water, 4186, changing T again. Are those changes in T's going to be equal?
No. The water will most likely change more than... No. The
So
iron
you're
most
telling me I have
likely
two
change
variables then here, right?
more. Yes.
Uh-oh.
Did we just set them equal to the wrong thing then? Or-
I want to ask you how we resolve this. Can we figure this out? Is there a way? Is it doable?
There's no hope for us.
What do you think, Sue?
True.
200 minus x. Oh no.
We
0
need-
plus
we need-
x.
What'd you say?
200 minus x and 0 plus x.
200 minus x.
I don't know.
Yeah. Let's do that.
Oh,
See what happens.
it's not gonna work.
Minus,
Because
okay.
the x is
Initial
gonna be
temperature
different,
is
so it'll have to be x
200
and y, and it's
minus
gonna...
x
equals 4186, 0 plus x.
But then they can't both be x's because it's going to be a different number.
Right.
So I give up.
Well, we can do it proportionally.
There's other ways. Mr. Ernst likes it proportionally, but it doesn't have to.
Why?
be.
Okay, would it be proportional though?
Mm-hmm.
Why?
It's proportional to the mass given the specific heats.
Wait just a
You
second.
need help, Mr. G?
No, I don't.
Okay, just
What
checking.
is change in t?
T1 minus T2.
No.
I mean,
Final minus initial, right?
yeah.
What is the final temperature of these two?
The same?
It's the same. So TF is the same, right?
That's what it's the same.
Yeah. So
Okay,
I
so
can do not
that's-
200 minus x in that way, but
Yeah.
TF minus 200. And here,
TF.
TF minus 0?
So it's just TF.
Yeah.
Nice.
Okay. So it is the same variable.
Wait a second. Oh, well, okay. And here's the weird part. This is, and this is hard because we don't, remember how we said that these are both going to be positive values because energy is positive and not negative?
But the change in it can be negative.
Right, the change can be negative. We don't want that change to be negative. We want it to be
Why?
positive. Okay? And thus
So you
that
find
means-
the negative heat of the lost one because
Yeah,
I
because
mean,
there's not such a thing as negative heat.
yeah.
We always want T positive. So we take a large T minus a small t. Okay? We take the larger temperature minus the smallest, so we keep the change in temperature positive. So since this one is losing, that means we do 200 minus TF.
Wouldn't that change it?
Yes, the right way.
Oh. I see.
Now the tough part is understanding why that is. And this is weird because I just explained this to Dan on Friday, and I'm drawing a blank as to why again.
Give me help, or you need help? I mean, what is the question?
Why do we need the change in temperature to be positive on both sides?
You shouldn't. Is it absolute value?
Maybe it is. I mean,
It
it
might,
doesn't say that.
the initial equation might be absolute value, but because
This kills me. I just explained this to Dan on Friday, and now I can't figure out how I explained it.
what is that?
0?
It's
Yeah,
initial
initial
temperature, yeah.
I don't know.
We will confirm and get back to you that tomorrow. You may look at sample problem 10C. And you've already read the whole section, right?
Yeah,
Even the
right.
latent heat stuff. So you've talked, or you've already read about dispersion as well. Mass times latent heat of heat of vaporization heat of
They haven't learned latent heat yet.
well, it's in the section.
You guys know what latent heat is?
We should have read about it.
Yeah, but they didn't.
You're probably right.
I'm not probably right. I know these students well.
It's the energy transfer during a change of a substance.
Yeah.
That's weird.
You learned about it in chemistry, so you should know it already, but
That was a year ago.
however, when you read about something a year later, it usually rings a bell.
Usually.
So now let's actually read the section for tonight, please. And look at the sample problem. Latent heat is the heat. It takes energy to transfer, to change phase. So water, once it gets to 100, begins boiling.
Okay.
It needs heat to continue at the boil, but it also needs more heat to change from water into gas. So once it starts boiling, you continue adding energy to it, it stays at 100 degrees. Does that make sense? Boiling water is not at 113. Okay, even though you continue to add heat to it, it stays at 100. That extra heat that we're adding to it is used when?
Oh, I remember that chart.
Is used in phase change. It's used in phase change. You guys understand what I was saying or no?
Change of phase.
If not, continue to read, ask questions about it when you get back tomorrow, please.
We'll talk about this more, but
Let's go.
I remember this real quick. We know this has a negative temperature gain, right? Positive gain. This is like a negative gain, right? A loss is like a negative gain.
Sure.
Makes
Okay.
sense. So
Oh, so you just
our
put
TF
them
minus TI is negative because it's going to be losing temperature. Make sense? So we're just going to move that negative over and make it TI plus,
Yeah, the second one with
Yeah.
negative TN plus.
right? We're just going to switch it around, that's all.
Okay.
Negative TI plus.
Could be because of that.
Right,
Did
put
I
it over there. Yeah.
staple it in the wrong order? No, the machine stapled it. No, I don't know.
So just find the actual math change.
Two separate tests.
Thank you.
Okay. That's it,
You
yeah.
got AJ's too?
Yeah.
Sue's